Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the COMEDK Launchpad I am going to discuss about atoms and nuclei. Okay, so atoms and nuclei are slightly moderate important chapter, so if you have not studied it, go and study them because they are easier to score. Without much delay, let's start with today's session. First we are going to see a question. An electron of an atom transits from N1 to N2. In which of the following maximum frequency of the photon will be emitted? So first of all, we have to remember from Bohr's law, the energy associated with emitted photon is equals to h nu, and that is equals to the energy of the higher orbit, that is from where it is jumping, minus the final position where it is reaching. Okay, so from there we know that energy is proportional to the square of, inversely proportional to the square of the quantum number. For hydrogen it is exactly 13.6 divided by n square, right? But it is not mentioned hydrogen, so we are not using any, so we will use a normal constant. If it is an hydrogen it will be minus 13.6, but other than that it will be only simply 1 upon n2 square minus 1 upon n1 square. Okay, now there is a negative sign we have to include, otherwise it will give you a negative, the overall sign will be negative, which is not correct. So the negative sign of this negative sign we have to include here. So we get 1 upon n1 square minus 1 upon n2 square. Now remember that electron is jumping from 2 to 1. Okay, electron is here they have mentioned n1 to n2, so let me correct that. N1 to n2 means first will be from where it started and second will be where it landed. Okay, where it started and where it landed. Okay, so this is very important to remember. So n1 to n2, so they tried to confuse you. The question is actually easy. Okay, now if you simplify this, n1 to n2, so n2 minus n1. So if you just simplify this, you will get k into n2 square n1 square, and here will be n1 square minus n2 square. Okay, obviously from there we can see that value of n1 must be greater than n2. So value of n1 must be greater than n2, otherwise the frequency will be negative. Negative frequency does not make any sense, so that's why n1 has to be greater. So n1 has to be greater, either this one or this one or this one. These are the three candidates where we can get a value. Now we have to check which one is giving the maximum possible value for this, so that the frequency is maximum. Okay, so first we will use the this one, 2 to 1, easiest one. So k into 2 is 2 square, 4 minus 1 square divided by 4 into 1, so the answer is 3 by 4. So 3 by 4k, this is the value, that is 0.75, almost 0.75k. Now we will check the same thing for 2 to 6. Now 2 to 6 means 2 to 6 is not possible. 2 to 6 is not possible. 6 to 2 is possible. Okay, higher energy to lower energy is possible, not from lower to higher. They don't give you any radiation. It requires radiation to absorb. In this case it is absorption, in this case it is radiating. So in 6 to 2 we will check. What is 6 square? 6 square is 36. What is same formula we are using? What is 2 square? 2 square is 4 divided by 36 into 4. So you get this as 32 divided by 36 into 4. It will be 8 and it will be 4 by 9. So you get this as 4 by 9. Okay, so basically you can take, even if you take this 9 as 8, then it will be 2 by 4. So obviously 2 by 4 is smaller compared to 3 by 4. Okay, so the highest energy will happen, highest photon will happen when it is jumping from 2 to 1. Very interesting, right? So higher the gap does not always give you the higher energy difference. Okay, if it is jumping from 6 to 1, yes, that will give you a highest. That is no question asked. If the final orbit is same, okay, both cases, suppose both cases are 1, then higher the gap will be higher the energy. But if they are not having the same energy gap, smaller the lower orbit, higher will be energy gap. You have to remember that. Very interesting question. Suppose an electron is attracted towards the origin by a force K by R, where K is constant and R is the distance of the electron from the origin. By applying Bohr model to this system, the radius of the nth orbital of the electron is found to be Rn and the kinetic energy of the electron to be Tn. Then which of the following is true? Wow, very difficult question. So the attractive force is given. Which is attracted force? Attracted force means this is the centripetal force. Centripetal force means V square mv square by r, and that is given as K by r. Now from there r cancels, so we get V square is equal to K by m. Is that K is a constant? Mass is mass of the electron, thus they depend on the quantum number n. So velocity is independent of quantum number n. So that means kinetic energy, what is kinetic energy? Half m v square, that is half m K by m cancels, so you get this as half K. So this is a constant. So kinetic energy is independent. So you don't need to solve everything. Just check the kinetic energy. You will see that kinetic energy is independent of n. So this is the correct answer. Rn you can calculate from here. Okay, the relationship between velocity and r, from there you can calculate Rn is directly proportional to n. I am not doing that. I have solved the question by only solving the 50% of the part, right? Which of the following lines of the hydrogen atom spectrum belongs to Balmer series? Balmer series is basically visible range. So that is about 400 nanometer to 670 nanometer. Okay, in terms of angstrom, 10 will be more. 10 will be more in terms of angstrom, right? So angstrom is basically 10 times more than nanometer, right? So if you see the options, only one is falling in this range, that is this one. So this will be visible. Next, first Bohr radius of an atom with z is equal to 82 is r. Radius of its third orbit is. So we know that Bohr radius is given by n square by z square r naught. R naught is Bohr radius. Okay, z is the atomic number. Now it is given that for first Bohr radius of an atom is given by, for z is equal to 82. Okay, 82 actually will not matter over here because they will cancel, is r. That is, that value is given as r. Okay, they asked you what is the value of third Bohr orbit, that is r3. R3 is 3 square divided by 82 whole square r naught, that is 9 times r naught by 82 square. So you will get this as 9r. Very easy question. Okay, radius is directly proportional to n square. A gas of monoatomic hydrogen bombarded with a stream of electrons that have been accelerated from rest through a potential difference of 12.75 volt. The emission spectrum one cannot observe in any line of the energy is 12.75 volt, and if you see this, the energy will be E is equal to h nu. Okay, so this is the supplied energy. So what is the supplied energy? Supplied energy is 12.75 into 1.6 into 10 to the power of minus 19. From there the frequency range that you will get, or wavelength range, let us consider the wavelength. That will be easier for this question, right? One more thing, we will use a shortcut. What shortcut we will use? Let's see. Instead of calculating in terms of frequency, we will use hc by lambda equals to 12.75 eV. Okay, volt means EV, right? If you multiply with charge of electron, you will get that in EV. So lambda equals to hc by 12.75. Now what is hc? hc is 1240. 1240, our old friend, 12.75. Right, so 12.75, so you can cancel this and you get the lambda to be approximately 100 nanometer. Okay, so 100 nanometer means it is outside the visible zone, so it is basically Balmer series that you cannot see through this. Paschen, Lyman and Pfund can have this range, but Balmer is definitely not going to have this range. X-ray of wavelength lambda equals to 2 angstrom is emitted from the target of metal. The potential difference applied across the cathode and the metal target is. So you have to find the voltage. So again hc by lambda is the energy, right? And that should be equals to the whatever EV you have applied, voltage, whatever voltage, E into voltage you have applied, right? So you have to find this. Basically you have to find this. hc is 1240. Lambda is what? Lambda is 2 angstrom, that is 2 into 10 to the power of minus 1 nanometer, right? To convert it to nanometer, we have to divide it by 10. That's why there is a difference. Okay, so the calculations will be slightly different, but the method is same. 1240 divided by 2 into 10 to the power of minus 1. So it will be 6 to 20, and this 0 will go up. You will get 620 100. Okay, 6200. 6200 volt is the answer for this question. Easy question. Okay, only thing, just this conversion you have to be little careful. Okay, nanometer to angstrom multiply by 10. Okay, angstrom to nanometer divide by 10. Next, the best waves for emission of electrons from a surface. Obviously smallest the frequency, highest is the chance of electron emission, so X-ray is the answer. The de Broglie wavelength of an electron in the first Bohr orbit is equal to half. So de Broglie wavelength is basically 2 pi Rn equals to n lambda. That was the de Broglie's hypothesis about Bohr's quantum mechanics. Okay, Bohr's postulate, right? Bohr's third postulate. So he even derived that postulate from there. So for first order, 2 pi Rn1 equals to lambda. So for first order, the circumference of the first Bohr orbit should be equals to the wavelength lambda. Okay, equal to the circumference of the first orbit. Okay, equal to the circumference of the first orbit. Okay, so the de Broglie wavelength of electron in the first Bohr orbit is equal to circumference of the first orbit itself. Next, the amount of energy required to separate an hydrogen from a proton and electron is 13.6 eV. That is the ionization energy, right? If you want to disassemble it, that is the energy that we have calculated. Minus 13.6 eV is the energy at the ground state. If you provide exactly that much energy, the electron and proton will be separated. An electron in hydrogen atom makes a transition from n equals to 1 to n equals to 2, where n1 and n2 are principal quantum numbers of the two states. Assuming Bohr's model to be valid, the time period of the electron in the initial state is 8 times that in the final state. The possible values of the n1 and n2. So time period is basically proportional to n cube. Okay, time period of oscillation in an hydrogen orbit is proportional to n cube. Okay, so first state is 8 times. First state is 8 times means 8 times means n has to be equals to 2. So 2 cube is 8. So first state T1 must be 2. Okay, so n1 must be equals to 2 and n2 must be equals to 1. That is the only possible case, right? So it is okay, there may be some other cases. Let's see. 2 and 1 is not given. Other possible cases is okay. So let's see. T1 by T2 equals to n1 cube by n2 cube. okay, and this is given by 8. So N1 by N2 equals to 2. So we have to see which all are giving you this combination, that is N1 equals to 2N2. Okay, N1 equals to 2N2. So it is possible that in this case it is possible. Okay, N1 is 4 and 2 into 2 is also 4. So this is the another possible case. This one is not possible. This is giving you 4 times, which is not, it is only 2 times. The binding energy of deuterium 21H is 1.1 mega electron volt per nucleon, and alpha particle has binding energy of 7.1 MeV per nucleon. Then the reaction, this one, the energy Q is. So what is the energy of the deuterium? Deuterium has energy of 1.15 MeV. So 2 deuterium are merging. So 2 deuterium is merging means total energy has to be 1.15 into 2, that is 2.5. Okay. Now the binding energy per nucleon, this is the total binding energy. Okay, total binding energy. It is not per nucleon. But for helium, binding energy binding energy per nucleon is given, sorry. So total binding energy for the deuterium will be times 2. Okay, deuterium will be, because it has one proton and one neutron, right? So the total energy, initial energy of the system will be 5 MeV. And what is the final energy? Now it is has 7.1 MeV, 7.1 MeV per nucleon. How many nucleons are there? It has 4 nucleons. 4 nucleons. So this is the initial, and final will be 28.4. 28.4. So what is the extra energy that will be released? That will be 5 minus. So 23.4 will be released. 23.4, I think I made some small mistake, so that's why it will be 23.8 MeV. Okay, yes, I made a mistake over here. Okay, I made it 2.25, 2.5, it will be 2.3. Okay, and it will be 4.6. 4.6. So if you minus this 4.6, you get 23.8. Okay, correct answer will be this one. Next question, for mass defect of 0.3%, the binding energy of 1 kg material is. So 1 kg material, okay, and the mass defect is 0.3%. So it will be, the question is slightly odd. It is given also given in terms of erg as well. So 1 kg into 0.3 divided by 100, right? That is the meaning of 0.3%. So into mass defect is 1 kg into 0.3 by 100 into c square, right? C square is 3 into 10 to the power of 8 meter per second. Everything we are calculating in SI unit right now. If required, we will convert it into ergs. Okay, but right now the answer is in joules. It is a square. Okay, so obviously you will get this as 0.3 by 100, that is 3 into 10 to the power of minus 3, minus 2 from this, and 0.1 was there, we removed that point, so 10 to the power of minus 3 into 9 into 10 to the power of 16. So 3 9s are 27 into 10 to the power of minus 3 plus 16, 13, or 2.7 into 10 to the power of 14 joules. So correct answer is 2.7 into 10 to the power of 14 joules. The energy equivalent of 1 kg substance, 1 gram of substance is. So let's see, this is very easy. 1 gram is 10 to the power of 1 gram is 1 upon 1000 gram, that is 10 to the power of minus 3 kg, and into 9 into 10 to the power of 16, right? MC square. So directly I have used this previous question, we have used it, right? So c square is nothing but this. So 1 gram means this one. So it will be 9 into 10 to the power of 13. 9 into 10 to the power of 13 joules. Okay, correct answer is this one. So find the energy equivalent of one atomic mass unit joules and in MeV. So atomic mass unit in MeV is 931.5 MeV. Okay, 931.5 MeV. So either one of them is correct. Now what we already know this. Now how can we go and find unit in joules? Will we do the mathematics again? Nothing is given. We will use the reverse mechanism. What is the reverse mechanism? 931.5 MeV. This is the energy. MeV means mega, mega means 10 to the power of 6, but also EV. EV means 1.6 into 10 to the power of minus 19. Okay, so 900 into almost 1.6, okay, which will be 450, 1300, 1500, okay, almost 1500. If you multiply these two, you will get, you can check that out, 10 to the power of minus 13, or you can say 1.5 into 10 to the power of minus 10. 1 2 3, 1 2 3, so 3 reduced. So correct answer is this one. Last question, how does the binding energy per nucleon vary with the increase in the number of nucleons? Okay, binding energy per nucleon basically remains constant, but it is not increasing. It basically, if you see the graph, binding energy per nucleon, the graph is almost flat. Initially it increases up to some point, then it becomes almost constant, and then it decreases slowly. Okay, it is neither increase, so it first increases and then decreases. Okay, so this is the correct answer. First it increases binding energy per nucleon, it decreases, it becomes constant. Constant part is not mentioned unfortunately in this option. It is one of the previous year question, 2013 it came, long back anyway, but you have to remember that it increases and then becomes constant and then slowly decreases. So this is the correct answer, option C. Okay, I hope you enjoyed today's COMEDK Launchpad session, and whatever questions you have, you can mention in the comment below. I'll try to answer them as well as much as possible. I'll be see you in live session from Monday. So very good news for you. Monday onwards, whatever Launchpad session is happening, I may not be taking the Launchpad session on Monday, but whoever is taking the Launchpad session on Monday, don't forget to watch it live. Also, COMEDK crash course is live. If you have not yet purchased it, go and check that out. The link of the COMEDK crash course is given in the description. I'll be back with a new session. Till then, bye.